it's a kind of operator. It's telling you effectively just to integrate, right? So you're now sort of integrating over this volume with that wave function, or vector if you like, put here, and the second one, psi n, put here. Okay? So, well, here it is actually written out. So 3 bars, so by definition. So this bracket is just an integral, you know, the overlap integral of these 2 wave functions, psi m and psi n. Okay? And it gives you the result, you know, a bracket gives you a scalar, right? So it's just the scalar product or dot product of 2 wave functions. So when you see this, it's just a shorthand for this, okay? With these wave functions interpreted as vectors, seen as vectors. Okay. Now it's convenient because you can start doing a bit of math. For example, now this bracket is just a scalar, right? It's usually just a complex number. So if we conjugate the complex number, remember what that means? It means you take that number and you just, wherever there's an I, square root of -1, you change that to minus I. Okay. So if you conjugate here this bracket, you can rewrite that as the following. So without the star here. Now, over the volume, that's a real, so you don't conjugate that. But these wave functions, they're usually complex numbers. Remember, there's an I in the Schrödinger equation. So the solutions to the Schrödinger equation, your wave functions, tend to be complex functions. Okay. So now, if you conjugate the whole thing, so you'll conjugate this and you'll conjugate that. So star 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 star. But the integral, the overlap integral, this is starred anyway. So now you've got a double star, these 2, okay? So that just becomes the real. Well, yeah. No, it becomes positive. Like it's just minus I, and then you minus the I again. The I goes to minus I, so now you've got minus minus I, which is just back to what you started with. So if you conjugate twice, the I's just stay the I's, right? So you'll end up with this. Now, but this is these are just complex numbers. So complex number Z1 times Z2 is the same as Z2 minus Z2 times Z1. Okay? So you can just change the order of these 2, and then so you get this. Okay. But this, by definition, in terms of bracket, is n here, m. Right? So So summarizing, if you take a bracket and you conjugate it, effectively you just reverse these 2. So now, so if you conjugate mn, you will get nm. Okay, and that could be useful. Right? So that's a little bit of math that you can use later, but it's handy. Right? Now continue on with interpreting the wave function as a vector. Have a look. So have a look at this here. Here you have a superposition, right? You're adding wave functions, weighted, multiplied by complex numbers, and adding them. So this whole thing here is a superposed wave function. Now these complex numbers here, you can now look on these in terms of bracket and overlap integrals. You can now interpret, instead of them just being simple complex numbers, you can now interpret these CNs in the following way. so these CNs now, in a sense, become components, rather analogous to your unit vectors components. Remember your unit vector EI, EJ, EK along the axes, x-axis, y-axis, z-axis, and so if you interpret these wave functions now, let's say n is 3, so we're just 3 dimensions. Then so you'd have psi1, psi2, psi3. Now if you interpret these wave functions now as unit vectors, then these components here, in a sense, I can't really say length because we're talking complex numbers. So these are, in a sense, coefficients of these unit vectors. So watch what happens. So if we're talking in terms of just ordinary vectors, and we dot product a general vector v by one of these unit vectors em hat, so it makes a unit vector. So now v is just this in this form, where these are your unit vectors. Now we're talking n dimensional space. Before previous two sessions. Yeah, one session, previous session. We were talking in 3 dimensions. Now we're talking in n dimensions. So your v in general will be of this form. Okay. So these are unit vectors in n. You can't visualize it in 3 dimensions, but mathematically you can write it down. So imagine n dimensional space. So these are the coefficients for that unit vector in n dimensional space. Okay. So that is your v, and you're dot producting it with m. Okay. Now this dot product, they're unit vectors. Okay. And if n and m are different, the scalar product of those 2 unit vectors is 0, and if n and m are equal, then the scalar product, or dot product, same thing, is 1. Okay, so in other words, this ENEM is the delta, the Kronecker delta, right? Now the Kronecker delta is 0, except when n equals m, and in all other cases is just 0. Right? So when n equals m, this c here just becomes cm, and all the other c's get multiplied by nothing because of the Kronecker delta. So this here becomes just simply cm. Right? This cm is just one of the components here, and which component? Well, the coefficient in front of the em. One of these m's will take the value m. Right? Now that's just ordinary vectors in vector language. Okay, so by analogy, we can do something similar with wave functions, because we're correlating, linking, translating wave functions and vectors. Okay, so here is your psi. That's your general superposed wave function of this form. Okay. So this is your psi here. So you can plug that, put that into here, and so this now is a bracket. Remember, a bracket you can interpret as an overlap integral, right? As done here. Okay. And so that's your general wave function. Think of it as like a general vector, so you can sort of think of these two as the same thing. So a general vector, and this is a general wave function, and think of this particular wave function as like a unit vector. Right? So you've got a kind of one-to-one mapping between this unit vector and this wave function, and the general vector and the general wave function, or the superposed wave function. So this, which is just the overlap integral, this gives you this, and the result of that is just Cn, the coefficient. So it's one of these C's here. Okay. So using the bracket language, you can quickly find the coefficient, the component, if you like, of psi m